Hello everyone, welcome to lecture number 8, frequency deviation and its impact on a single area. In the previous lecture, we have discussed about the turbine speed governing system, so which includes so important components like flyball speed governor, hydraulic amplifier, linkage mechanism, speed changer. After that, we have developed a mathematical model for speed governor, turbine, and then generator and load model. So once we obtain these three models individually, we have combined them together so that we have represented the complete block diagram for the single area load frequency control system. By using that block diagram or mathematical model, we can do performance analysis under various cases. In this lecture, we are going to discuss about frequency deviation and its impact on a single area. And this topic can be divided into two subcategories. One is steady state analysis, after that dynamic analysis. And whatever the block diagram or mathematical model we have developed in the previous lecture, that has been shown here in the figure 2.6. It represents complete block diagram model of a load frequency control for isolated power system. Or you can think this as a single area power system. Single area power system. So here, the first block, this one represents the transfer function of a speed governor, and the second block, Kt by 1 plus Tt into S, represent transfer function of a turbine model, and then Kps by 1 plus Tps into S represent transfer function of generator and load model. Delta Pc of S represent the command change in power, and delta F of S represent the steady state frequency deviation in frequency domain. And here R represent speed regulation of the turbine. So now, for the purpose of doing steady state analysis, we are going to consider a simple situation in which the speed changer has a fixed setting, that is delta Pc of S. Here we have two important incremental inputs for the load frequency control system. One is delta Pc and another one is delta Pd, where delta Pc is called the change in speed changer setting and delta Pd is called the change in load demand. So as you can observe in the complete block diagram, this is one of the input, that is delta Pc of S. This is the first input, let's say, and the one more input in this block diagram is delta Pd of S. So now to get the response delta F of S for these two inputs, I'm going to make use of superposition theorem, so which we use in solving multi-source networks or circuits. So here we have two inputs, delta Pc of S and delta Pd of S. So what we can do now, we can consider any one input at a time and deactivate other input. Then we'll try to derive the equation for output frequency response. Let's say in the case 1, we are going to neglect this delta Pc of S and consider delta Pd of S, then derive the response for frequency. And in another case, consider this delta Pc of S and neglect this delta Pd of S, then also you derive the response for delta F of S. Once we obtain individual responses, as per the superposition theorem, when these two inputs act simultaneously in the system, then we can get the response for delta F of S by combining individual responses. So let's move in that direction now. So now consider the situation in which the speed changer has fixed setting. That means there is no change in the delta Pc. There is no change in the command power Pc. So that means now we are going to deactivate this delta Pc of S. So neglect this delta Pc of S and consider this delta Pd of S. So this kind of operation is called as free governor operation, because we are not going to incorporate any change with the help of speed changer. So that's why it is called free governor operation. So in this operation, the steady state in system frequency for a steady change, for a sudden change in load demand by an amount delta PD of S, which can be expressed as delta PD by S, is obtained as explained in the coming slides. Here, the block diagram can be modified so that it can be suitable for case 1, where in the case 1, we are neglecting delta PC of S, that means delta PC of S is equal to 0, and we are considering delta PD of S that can be expressed as PD by S. So for this case, here there is no input, so you can neglect this, and this is the only one input and this is the output. So now the system is acting like a single input and single output block diagram. So for this case, you can derive the transfer function by using block diagram reduction rules. So the transfer function can be defined as the ratio of Laplace transformation of output divided by Laplace transformation of input. So here delta f of s is the output. So you can write formula for output as output is equal to input into transfer function TF, where you can rewrite this as transfer function is equal to ratio of output and input. So by using this simple formula, we can express delta f of s as, provided the condition is by neglecting another input, that is delta PC of s is equal to 0, then you can derive this formula. So once there is no input from this point, delta PC of s is absent, now these two blocks are in cascade connection. So as per the block diagram reduction rules, what we study in control system course, you can combine these two just by multiplying these two transfer functions. So that means these two blocks can be represented by using a single block whose transfer function is nothing but KSG into KT by 1 plus TSG into S multiplied with 1 plus TT into S. Now this is acting as an input here, and of course we are not supposed to ignore this negative feedback because here minus symbol is there, and with a feedback of 1 by R, and this is one more transfer function KPS by 1 plus TPS into S. So now once you combine this block diagram, you can get this equation. So let me give the standard formula. What can be used to get this one here is, suppose if there is a gain G, and let's say you are giving an input here, and let's say you are giving negative feedback with the feedback H, and if this is the output and this is the negative feedback system, then transfer function can be defined for this block as G by 1 plus G into H. Suppose if this is a positive feedback system, then here you will get negative. So based on this simple formula, what we studied in control system course, you can derive the expression for delta f of s. So once you obtain this delta f of s, now we want to do steady state analysis. So after some time at the steady state, what will be the value of frequency deviation? So that can be determined by using this rule or this formula, delta f at steady state and at the same time delta PC of s is equal to 0. It is given by the formula s into delta f of s, where s tends to 0 and provided delta PC of s is equal to 0. So once you substitute this delta f of s here and apply this formula, this 1 by s is there already in delta f of s, and here we are multiplying with s, so 2s which will get cancelled, and at the same time you have to substitute s is equal to 0 here. So once you substitute s is equal to 0 here, this term will become 1 plus TSG, and this another term will become 1 plus TT. But here we are keeping s is equal to 0, then 1 plus TH into s will become 1, and 1 plus TT into s will become also 1. So finally, you are going to get the equation as KPS by 1 plus KSG into KT into KPS by R into delta PD. So while the gain KT is fixed, so here KT is called turbine gain. So fix the turbine gain, and also KPS is fixed for the power system. And then KSG is easily adjustable by changing lengths of the various links, what we have seen in the speed governor. So out of three gains here, we are going to fix these two gains, KT as well as KPS, and we are going to play with only by changing this KSG, because this KSG can be changed very easily just by changing the lengths of the various links available in the speed governor, what we have seen in the previous lecture. And we are going to adjust this KSG in such a way that the product of KSG into KT is approximately equal to 1. So once we implement this rule, then that particular equation, whatever we have derived for delta F, will be changed to minus 1 by B plus 1 by R into delta PD. So where B is some constant, and it can be determined by empirically. So it can be determined by empirically. And this B can be expressed as dou PD by dou F divided by PR, where PR is nothing but rated power of machine. Rated power of our synchronous machine. So the synchronous machine, what we are using in the power plant, so that power maximum rating is nothing but this PR. So once we divide this with PR, the value will be converted into per unit. So this particular equation 2.17, delta F is equal to minus 1 by B plus 1 by R into delta PD will give you the steady state changes in frequency caused because of changes in the load. Because we have derived this formula by considering delta PD and by neglecting delta PC. So that is the reason this particular equation will give you steady state change in frequency due to the resultant of load demand changes. So now here the speed regulation R is naturally adjusted so that the changes in frequency are so small, usually in the order of 5% from no load to full load. Because we don't want to have very much variations in the frequency, because so many loads in the power system are sensitive to the frequency changes. So therefore, the linear incremental relation, this particular relation 2.17, can be applied from no load to full load. So just by understanding the figure 8.7, what we have seen, the linear relationship between frequency and load for free governor operation with speed changers set to give a scheduled frequency of 100% at full load. So now the droop relation can be expressed as delta F of S is equal to minus 1 by B plus 1 by R into delta PD. So this, using this particular equation, we can draw the graph as presented here in this figure 2.7. So take the load on x-axis, the percentage load is taken as on x-axis, and take percentage frequency in y-axis. So when you keep on increasing the load, by natural tendency, the speed of the machine will come down, then frequency also will come down like this. And similarly, at some other speed changer setting, suppose let's say there is 100% of load, here also, as long as the speed is decreasing due to the increment of load, the frequency is falling down. So in both the cases, for different percentages of loads, the characteristic is maintaining a droop nature, droop behavior. It is following the downfall trend. So here, the linear relationship between the frequency and load for the free governor operation with the speed changer setting to give a 100% schedule at full load is droop characteristic. And that particular curve, droop, or can also be called as slope, can be expressed as minus 1 by B plus 1 by R. So now this particular equation is in the form of y is equal to m into c, m into mx, m into x, where x coordinate is nothing but our delta PD and the y coordinate is nothing but our delta f. So this minus 1 by b plus 1 by r is nothing but our slope. So now the power system parameter b is generally much smaller than 1 by r. So typically the b value is 0.01 per unit megawatt per h, and 1 by r is approximately equal to 1 by 3, so that you can neglect this b. So once we neglect b here in this formula, we can do the modification as delta f is equal to, it will become, once you neglect this b, this 1 by r will come to the numerator. So then this equation will change to minus r into delta PD. So now the droop of the load frequency curve is thus mainly determined by only the regulation, the speed governor regulation. So how much droop you want to have in the characteristics, that can be possible only by playing with the speed governor settings. So that is a important summary point by having this relation. It is also observed from the above that the increase in load demand is met under steady conditions partly by increased generation due to opening of steam valve and partly by decrease in load demand due to drop in system frequency. So what we have considered in deriving this so-called equation is, we have considered that the load demand is changing. So whenever the load demand is changing, obviously you have to meet that increased load demand by increasing the power generation. So that power can be increased by increasing the steam input, just by opening the steam valve with the settings of speed governor. So from the block diagram, you can also express as delta Pg is equal to minus 1 by r into delta F. So just now we have derived equation for delta F as minus 1 by b plus 1 by r. So if you substitute that, minus into minus will become plus, then the equation will change to 1 by br plus 1 into delta Pd. So now the decrease in the system load is given as b into delta F. So that will become br by br plus 1 into delta Pd. So this belongs to case 1. Now let's consider another case where consider now the input delta Pc of S, which is expressed as delta Pc by S, and neglect the another input, that is delta Pd is equal to 0. Delta Pd is equal to 0 means, that means we are supplying power to a constant load. We are giving a constant power to the load and we are changing the speed changer setting. So in this case, from the block diagram, the way how we have derived output equation for delta F of S in the case 1, similarly we can derive a formula for case 2 as delta F of S at delta PD of S is equal to 0 as KSG into KT by KPS whole divided by 1 plus TSG into S into 1 plus TT into S plus 1 plus TPS into S plus KSG K2 KPS by R into delta PC by S. So again, if you want to have steady state frequency value, then we have to use this formula. Substitute now delta F of S here. In delta F of S, already we have 1 by S here. So this 1 by S will get cancelled by using this S. And at the same time, substitute S is equal to 0 here. So once you substitute S is equal to 0 here, this particular equation will change to KSG into KT KPS by 1 plus KSG into KT KPS by R into delta PC. So the first three terms, all these three terms will become equal to 1 because of substitution of S is equal to 0. So just similar to the case 1, again you can substitute the product of KSG into KT as 1. Then this particular equation will modify to delta F is equal to 1 by B plus 1 by R into delta PC of PC. So now if the speed changer setting is changed by delta PC while the load demand changes by delta PD, the frequency change is obtained by superposition. So that's what I mentioned at the beginning. So now we are going to combine the two inputs. When the system is having two inputs, both delta PC and also delta PD, the response is expressed as sum of individual responses based on the superposition theory. So then the final response we will get for delta F as delta F is equal to 1 by P plus 1 by R into delta PC minus delta PD. So here, from this equation, we can make an important observation as we don't want to have any frequency deviation. That means we want to maintain this delta F is equal to 0 always. So that you can have the actual frequency is exactly equal to the nominal value, that is 50 Hz. So this delta F will become 0 only when delta PC is becoming equal to delta PD. So that means when delta PC is equal to delta PD, we will get delta F is equal to 0. So which will show that the frequency change caused by load demand can be compensated by changing the setting of the speed changer. So that means whenever there is a change in the load, simultaneously you have to change the speed changer setting in the speed governor until the delta F value will become equal to 0, where delta PC also will become equal to delta PD. So here in this figure 2.7, as I explained, you can have 100% rated load, one curve is there, and 60% rated load, one curve is there. Both the curves are having same droop. That means same slope, that is expressed as minus 1 by B plus 1 by R. Approximately, you can express this equal to 1 by R because you can neglect B as it is very, very small. So that's about steady state analysis. Now let's discuss about the dynamic response. So to obtain the dynamic response, giving the change in frequency as a function of the time for a step change in load, we must obtain the Laplace inverse of the earlier equation. To get the dynamic response, now we are going to apply a step change in the load. Before that, we are going to reconvert this frequency domain equation into time domain. So the characteristic equation being of third order, now you can see here the denominator equation. It is of having highest power 3 for S. So that's why it is third order system. The dynamic response can only be obtained for a specific numerical case. So that's why we are going to substitute the typical values of time constants, TSG as 0.4 second, TT as 0.5 second, and TPS as 20 second. And here you can observe the TSG is much lower than TT and which is much lower than TPS as well. So here let TSG and TT is equal to 0 and this, at the same time KSG into KT is equal to 1. Then accordingly the equation can be modified as 2.23. Now in this equation, if you apply inverse Laplace transformation, then you will get the expression for delta F in the time domain. And the corresponding block diagram also will change to figure 2.7, where substitute TSG and TT is equal to 0 and KSG into KT is equal to 1. Then these two blocks are going to reduce to one single block whose gain is equal to 1. And this is the final equation 2.24, which will give you the dynamic response for the steady state change in frequency. So for these values, when you take R is equal to 3 and KPS is equal to 100 and TPS is equal to 20, delta PD is equal to 0.01 per unit. These are the only some considered example values just to draw this graph. So once you substitute all these values, you will get delta F of t as minus 0.029 H. That means continuously our load frequency control will offer some steady state frequency error. So because of this steady state frequency error, our actual frequency may not be equal to the nominal value, that is 50 H. So you can observe that same variation in the graph also. The actual steady state frequency deviation is keep on making some vibrations and settling to some error value. So this is nothing but our error value, that is equal to delta F of t. As per these values, this value is equal to minus 0.029 H. So now this is the problem. Actually, this is not the desired response because We don't want to have delta F value. We want to make delta F is equal to 0 so that the actual frequency will become equal to 50 Hz. So for that, definitely we have to take care of incorporating some controllers. So because of that reason only, now we are going to incorporate a proportional plus integral controller. So that means PI controller. We are going to take the help of PI controller here. So now accordingly, the block diagram can be modified like this. So here we are going to add PI controller whose transfer function is expressed as Ki by S. And for this PI controller, we have to give our frequency as the input. So that's why we are going to make help of frequency sensor. Sense the frequency value and give that frequency value to the integral controller. So once you give that to the integral controller will do some corrective action in the block diagram by giving some error signal or correction signal, so that ultimately our objective is to achieve this delta F is equal to 0. So that can be possible only when you incorporate this integral controller in the block diagram. So now let's see what are the changes in the mathematical equations after incorporating this integral controller. So now the signal PC of delta PC of S generated by the integral control must be opposite sign of delta F of S. So earlier when integral controller is absent, here the signal is delta PC of S. Now after incorporating this integral controller, this delta PC of signal, whichever is acting as the input, is coming out of this integral controller. So that sign should be opposite of this delta F of S. So now the transfer function can be derived as, from the transfer function, the output delta F of S can be expressed as like this. And it can be simplified to 2.26. So by using this particular delta F of S, if we observe the controller response, now the frequency, steady state frequency error is coming very close to x-axis, and after certain duration of time, it may become exactly equal to 0 also. So now you can have two different cases in the same graph. The dotted line represent the response without integral control action, and this solid line represent with integral control action. So without integral control action, here this offers always some delta F value which is not equal to 0, and F is also not equal to 50 H. But once you incorporate this integral controller, what is happening here? The delta F, the steady state frequency error, is making some oscillations, and after a certain amount of time, it is becoming equal to 0. So that means delta F is becoming 0, and then actual frequency will become equal to 50 Hz. So to reduce this steady state frequency error only, we have implemented this PI controller in the block diagram. So that is the importance of application of PI controller. In the control system, we might have studied the PI controller is used to reduce the steady state error. So that kind of application we have implemented here in bringing frequency value exactly equal to 50 Hz by making delta F is equal to 0. So this lecture can be summarized as, we have derived expression for steady state analysis and for dynamic response also. And then we have made approximation in mathematical equations by taking some numerical values. And then we have incorporated proportional plus integral controller, because of which only we are able to achieve delta F is equal to 0 and our nominal frequency equal to 50 Hz. If it is an Indian grid system or if it is a US grid system, this frequency can be made equal to 60 Hz. So this particular controller, PI controller, is made our duty so easy so that we can control the frequency irrespective of load changes. Because in the real power system, continuously the load will keep on changing. Whenever the load changes, the speed of the machine also will try to change, then frequency also will try to change. But still we are able to obtain this frequency equal to nominal value only because of the action of this PI controller. So that's what we have studied in this lecture. So we'll meet in the next lecture. Thank you all.